Okay. Good morning. Good morning. Welcome. I guess, so thank you to our volunteer, Sophia, who's going to be in charge of the microphone. So how's it going so far? Anything interesting and recent?
No questions yet, but there's a post on
All
discussions,
right.
guys.
Awesome. So all of you can, choose to either shout it out or type it into the ed discussion under the classes, and Sophia can read it out with her microphone. And then, actually, if it's read on the microphone, it's easier to hear on the video as well. So, and hi, video people. Yeah, so let's finish. Do you remember what we were doing last time? We had the ye old ladder slipping question. This is as far as I got. So there was a uniform ladder leaning against a frictionless wall, so there's no friction up there, but it's a friction-y floor. So when I drew this out, I had no static friction force for this point 1, where it's in contact with the wall, but there is a friction force at point 2. And I reasoned that since the ladder probably wants to kind of slip to the right, then I would say that the static friction force is to the left. That's a guess. If I were to, I guess, compute the static friction force to be negative after I do all my equations, then I would know that I picked wrong. And that'd be okay. But so basically, there's 3 equations, which is the sum of all the torques is 0, the sum of all the forces in the y direction is 0, and the sum of all the forces in the x direction are 0. So 3 equations is plenty to solve out whatever you're trying to solve for, which is mu sub s, I think. So let's just write down this, the sum of all the torques is 0. It's going to be, let's do this one. So that one's going to be N1 times this D1. And then, so wait a second, but is it negative or positive is the question. This is, so the rotation axis is down here. The normal N1 is trying to rotate it, I think, clockwise. So that's a negative torque. And it's the force times the lever arm. And the lever arm's D1. Next one we could do is gravity. So, and I don't know if it's positive or negative, but let's just write it down. mg times dg, that's the lever arm for the gravity. Now let's think about this. If it was only gravity pulling down about this rotation axis, it would rotate the thing counterclockwise, so that's a plus. And then we've got, the normal force, too. It has no lever arm, and the static friction has no lever arm. And those are the 4 forces, so it all sums up to be 0. And if you kind of get rid of the zeros there, you can solve that N1 times D1 is equal to m times g times dg. And I think I'll just put a box around that and call it equation 1, because I'm going to use it later. The other things you need to consider are the y components of the forces. Those should sum up to be 0. So N1 has no y component. Mg has got a negative mg. N2 is plus. And the static friction is horizontal, so that's it. So you can solve that for N2 is equal to mg. It's kind of a familiar looking equation. And then the sum of the forces in the x direction also have to equal 0. So the only 2 x component forces are N1 in the plus x direction and static friction in the other direction equals 0. So you got N1 equals the static friction force. I'll call that equation 3. And we can combine equations 1 and 3 to get that the FSD1 equals mg times dg. I just substituted in the N1 to that top equation. And then what are we trying to do again? We're trying to solve for mu sub s, right? So let's try to get there. Let's use that Fs is equal to Fs max, which is equal to mu sub s times the N2, which is the normal force on from the floor. don't get the normal forces mixed up. This means that mu sub s times n2 times d1 is equal to mg dg. I'm going to combine this with equation 2 over there. I've got mu sub s times m times g times d1 equals m times g times dg. So that's good. Now all we have, well, we have m and g, which we don't know, mass of the ladder, but it's on both sides of the equation. G is on both sides of the equation. We can just divide both sides by m, divide both sides by g, and now we've got it in terms of things we actually know. So mu sub s is equal to dg divided by d1. So it's 1.5 over 2, half that horizontal distance, divided by 2. And these are in meters and meters. So you get 1.5 meters divided by 4 meters. You get mu sub s is equal to 0.375. Or I guess I could round it, 0.38. So to me, it's good that this is good that it's greater than 0 and less than 1, because these normally don't come out to be more than 1. And this, by the way, is the minimum mu sub s for no slipping, because I set Fs equals Fs max to be just about to slip, and then solved it as an equilibrium problem. Oh goodness, you guys are all over the place here. It's like the same distribution of seats, but there's just fewer students. So I'm going to actually ask you this question on learning catalytics. This won't mean much to you people in the, where's it here? On the video. But I'm a little curious as to where you're sitting. So this is a map of Con Hall, which shows the floor, you guys down here. Not the actual floor, but your chair is on that flat part. There's the tiers, where the wave tends to really happen. And then there's all the 2 levels of balconies. So where are you sitting? A little curious? Yeah, you're actually on the literal floor. And we can sort of see. Oop.
So we have a quick question about the term test.
Oh yeah, sure.
Is the material covered on the Monday after reading week going to be on the term test?
Yes.
Okay, thank you.
But you'll have 30 hours to absorb it or something like that before you're tested on it, because it'll be from noon until 6 p.m. the next day, I guess. So I think that's fair enough. But yeah, we're going to finish up. So this is kind of what we're looking at. The floor, the tiers, and then all these people in the balconies. People not here. That's interesting. People not sure where they are. That's also kind of interesting. That's okay. But I guess my point is just that there's 253 people in here. Almost all of you could be on the floor. And if you include the tiers, there's like, the total non-balcony seats is 760 for a class that's got 250 people in it right now. But the main thing is, okay, so another thing, we're almost at reading week, starting at the end of today. I'm going to be doing other things. I've got a bunch of public outreach stuff. I'll be around, so you might see me with my office door open if you're desperate, or you could email me or something. But I'm not going to have those office hours. And so the next question, I stopped delivery. Not for marks or anything, but I want to take 2 minutes and hopefully everyone here, and I want you to do this every time you come to Con Hall, sit beside some other human being. This is, you got to pair up. This is a discussion-based class. That's what all these learning catalytic questions are supposed to be about. It's supposed to give you a chance to talk to someone else who's doing the same term test as you are on Tuesday, right? And who is doing the same homeworks and is in the same boat as you. You got to meet these people or you won't be able to find any help. The only way I got through first year physics was I had about this many friends, like 8 or something like that, friends roughly, that I could talk to that were doing the same problem sets as me and that we could kind of help each other out. This is how you learn physics, or even math, I think. Let me give you 2 minutes and tell me something interesting about a neighbor. So I know, sorry. I will do that thing, the rolly thing. I guess I have to do the camera and video. No, just do that thing. We do have the recording. Yeah, that's true. If you see a lonely soul who's not talking to anybody, maybe reach out. And feel free to reseat yourself if you need a partner. Okay. Okay. So neither of these first 2 questions are going to count for points, actually. They're just sort of more for fun. And to give you the idea, once again, I like you guys to pair up during class. Sit beside somebody. It's good practice in all your classes. Or I saw some teams of 3 around here, which is fantastic. Okay. So we're going to talk about center of mass. We have a demonstration that Pius is just going to go get one more piece for. It's one of these things, there's a lot of times, like the conservation of momentum, they make it look so complicated in the equations, but really it's just P initial equals P final. And I've had students come to my office and are, I don't know where to start. Well, P initial equals P final. Oh, yeah, right. You know, it's actually simple. And this is kind of another thing. It's like that. Looks terrible, doesn't it? But it's really not that bad. You're just multiplying a position times a mass for however many particles. There's usually like 2 particles. And then you divide by their total mass. So they make the equations look just about as nasty as they can. But when you actually do a real example problem, it's really not so bad. So I'm going to do that. Basically, calculating the center of mass, it's sort of like calculating your grade point average. So if you have H courses, they count half as much as Y courses, right? So you multiply by the number of credits that you're getting. So in this case, the position matters, but also the mass of the particles. You multiply the positions to find the position of the center of mass. You multiply it as a weighting factor, the mass of all those particles. So I'm going to give you, I have to cut you off with this describing your friend, because I'm giving the real first actual question, which is worth a point. 0.8 for answering anything, and another 0.2 for getting it right. So I think there's one answer here, either A, B, C, or D, which would be the center of mass of this object, and you neglect the mass of the stick. So you got a 6 kilogram mass on the left and 8 kilogram mass on the right. Those are your particles. Find the center of mass using that crazy equation. And I'll just write it down if you want. Okay, do you want a hint? First step is to define an origin, right? You can't have an x-coordinate unless you have an x-axis. But you can define your origin wherever you want. I don't know what the easiest thing is. Maybe you could draw it right here. That's where I'll probably put it. But it doesn't matter where you put it. There's y, there's x. So this would be right here, x equals 0, right? You have to do that, or else you can't have positions of things until you've defined your axis. After that, should be easy. This is a good time to check with that neighbor you just made friends with. See if they got a hint. Do you remember what capital M is? Capital M is 8 plus 6. Give you 30 seconds. Click in. Okay. All right. 5 seconds. 4, 3, 2, 1. Survey says a lot of people are answering that point C is the center of mass of this system, which I agree with, but let's do it. So it's just x center of mass, so it's going to be 1 over 6 plus 8, because that's what m is, times 6 times 0, because that's the x-coordinate of that one, plus 8 times 0.7, right? You guys see where I got that? This is x equals 0.7 meters. So it's just going to be 8 times 0.7 divided by 14. I got that it was 0.4 meters on my calculator. And so it's 1, 2, 3, 4. Something like that. Do you want to take a look at the discussion board? You're good? Okay. And I guess I could throw the hammer. Pius isn't back yet, but we can do this one. An unconstrained object, i.e. one not on an axle or a pivot on which there is no net force, rotates about a point called the center of mass. Center of mass remains motionless while every other point undergoes circular motion around it. So this is if there's no gravity. I might be able to show you this so not this one yet, but this hammer. So I got a hammer about which there's a center of mass, and the idea is that if I put my finger right under the dot, it should be pretty much balanced. It's a little bit hard to do. Like that. Whoop. So just about. So that's the center of mass. And then if I throw it, let's go back, because you won't be able to see this on the laptop, I don't think. But maybe the video guy will. You ready? You got me? I'll try to throw the hammer and see sort of, whoop. I'm a bad catcher. But idea being that the center of mass point kind of just goes straight up and straight down. Let's see if I can catch it this time. Sort of. Okay. So that's where you've got a parabolic trajectory of the center of mass while the thing rotates around that center of mass. So again, it's that point particle approximation, I guess, the model, which is that gravity pulls the whole object as if it's sort of hooked at the center of mass. And then, so the gravity doesn't have any torque around that center of mass, because that's the point where it's applied. So that's why things rotate around that point. So gravitational torque, that's the thing. Actually, we're ready. Want to do it? Here's another good one. This is, again, about center of mass, all this stuff. So let's go to aux plate. We got one more cool demo. So basically, this one is just showing how if you take this rail and you release it, what happens is the center of mass rolls down, which is to the left. Sorry, yeah, to the left. Okay. If you put this one on, it rolls the other way. So what's going on there? What's going on is that there is a sort of a tapered rail which gets higher, but it's tapered so that the center of mass of this thing is actually lower when it's over on the right side than it is on the left side. So it rolls uphill because, I guess, as it goes along, it falls down until it gets to there. So that's showing that the center of mass kind of seeks out the lowest position. So it's another good reason why center of mass is good. Thank you so much, Pius. Nice day for a walk, I guess, right? I'm always... Oh yeah, okay, so gravitational torque. So one of the points of finding center of mass was so that I could balance the hammer on my finger. So what that means is that it doesn't rotate because the torque from the gravity is 0 about that pivot point. So when calculating torque due to gravity, you may treat the object as if all its mass were concentrated at the center of mass. And then this would be like your lever arm of the gravitational force, if this is the axis of rotation. So there's sometimes people ask the question, with this bread knife, let's say, which side is heavier? Is there more mass to the left of your finger or to the right of your finger? That's a question. And it could be even a test question, I guess. So what the trick here is, choose the support point is the center of mass. And in fact, you could even do this equals center of mass. And if you set this to be equal to the axis of rotation, then you know that the finger does not apply a torque. Axis of rotation. And so the sum of the torques equals 0 just looks like, if this is like x1, some small distance between here and the center of the wooden handle, and where we have a very thin metal knife, so it's a thick handle and a thin knife, so that x2 is larger than x1. That makes sense. I guess metal is more dense than wood, but you've got more density, I guess, along in the handle than you have in the metal. So you've got something like, this would be M1G, and this would be M2G. So you've got M1G times X1 and M2G times X2. But the question is, are they positive or negative? So you have to, again, look at which direction around the rotation axis it wants to rotate the object, clockwise or counterclockwise. So the M1G seems to be counterclockwise. So that's a plus. And the M2G seems to be clockwise, so it's a minus, so that's okay. It's good that one's plus and one's minus because they have to cancel each other out. So you end up with M1, you can, I guess, divide both sides by G. M1 times X1 equals M2 times X2. So M1 divided by M2 is equal to X2 divided by X1. So X2 is greater than X1 means that M1 is greater than M2. The handle is heavier. There's more mass to the left than there is to the right. Okay. Make sense?
A quick question about finding the center of mass.
Yeah.
Does the equation work for finding the center of mass in both the x and y components? So is center of mass a 2D concept?
Yeah. Yeah, exactly. So if in a lot of these questions I've done one-dimensional, so linear objects that don't have a y extent. But yeah, if you have y coordinates of different particles, then you can also compute the y center of mass. It's sort of like these vector equations. It's just there's two equations that look very similar, one for all the x's and one for all the y's. So it's a really good point. It's a 2D concept. But I think all the examples there are 1D. Let's do another one. So you guys do this one. Two objects of masses m and 2m, so one's twice as heavy as the other, are hanging from opposite ends of a uniform horizontal beam. The beam is supported by a string at its center, and the objects are balanced. So which of the following must be true? So if they weren't hanging on the beam at all, then the beam wouldn't rotate because it's a uniform beam supported at its center. But now they're not necessarily at the very opposite ends. They could be at different distances. Okay. But opposite sides of the string, I think, is what I mean there. So the question is, are they at the same distance from the string, or are they different distances? Let's draw it. Okay, 30 seconds to click in your guess. See if you got an intuitive feel for this yet, and then I'll try to solve it. Check your neighbor. I'm glad to see most of the people on the balcony are paired up. That's good. Okay. I was thinking if you want to be alone, you could go back to COVID and still be in your dorm room, right? You're here to meet people. Going once, going twice. Stop. So a lot of the class is voting for the object of mass m is twice the distance from the center of beam of the object of mass 2m. So, and I like that answer as well. But let's just say I don't know it. What can you do? Well, you could just draw them, m1g, and draw m2g and solve this out, right? Let's pretend I don't know. So there's x2 and there's x1 being those distances. So sum of the torques is equal to 0. It's going to be m1gx1 and m2gx2 equals 0. Now you got to check if they're plus or minus. The rotation axis I put at the string because I don't want to take into account the torque of the string, right? So if the string is at the rotation axis, its torque is 0, so I don't have to worry about that one. M1G seems to want to pull it counterclockwise, so that's the plus. And M2G seems to want to pull it clockwise, so that's the minus. Anyway, they're opposite, so that's good. Divide both sides by G. Doesn't matter. And you get, once again, that M1x1 equals M. So equal torques, but equal magnitude torques on either side, but opposite direction. Sorry, let's do x1 over x2 is equal to m2 divided by m1. It's 2m divided by m. So x1 equals 2x2, twice as much. Okay. And we are doing great for time. So this is the whole big idea of static equilibrium problems, is that in equilibrium, an object has no net force on it and no net torque. So you draw an extended force diagram and show where each force acts on the object. You define your XY axes, choose a rotation axis, and these can be tricky. Sometimes you have to make the right choice, especially that rotation axis. I often try to put it at some place where there's a lot of forces I don't care about, so I don't have to compute their torques. Each force has three things. It has an x component, which might be 0, or might not be. It has a y component, which also might be 0 or not. And it has a torque, okay, which also might be 0. And you just sum them all up for all that. If you've got 5 forces, you're going to have 5 x components, 5 y components, and 5 torques. Okay. But they all have to sum to 0 if the thing's not accelerating or rotating. So, and those are the equations. Let's do another example. This one from a past term test. It's kind of a chapter 8 equilibrium question. A uniform meter stick of length L equals 1 meter has 0.2 kilogram mass suspended from a string from its left side and rests on a pivot that's L over 3 from the left side. If the system, consisting of the meter stick and the hanging mass, is in equilibrium, what's the mass of the meter stick? So, I think there's going to be a center of mass, mg, right there. And let's define rotation axis to be right there, I guess. Rotation axis. So L over 3 is that distance. I think this distance is going to be L over 6. by some geometry or something like that. So the sum of all the torques is equal to 0. It's just going to be is equal to, if this is like M1 or something like that, and this is M maybe, M is the meter stick, then you've got M, so 0, M1 G times L over 3, and M of the meter stick, G times L over 6. But let's do the minus or plus signs now. It looks like the hanging mass is going to pull the whole thing counterclockwise, so I'm going to put a plus there. And the meter stick, if it was just by itself, gravity would pull it clockwise, so that's a minus sign there. Those are those individual torques. So that's kind of it. I guess you're going to divide by G on both sides, which is a nice thing to do. And then try to gather terms. So I've got 0.2 times L. Actually, I can divide both sides by L pretty soon. Equals the mass of the meter stick times L over 6. Divide both sides by L. And I got the mass of the meter stick is equal to 6 divided by 3 times 0.2 kilograms is equal to 0.40 kilograms. So I got E. Okay, let's do another learning catalytics, shall we? Let me give you guys the ye old diving board example. We're good? And I'll post this up in a couple hours. Okay. Man is standing on a diving board. The board is fixed at 2 points, 1 and 2. So what are the forces of the piers? If these are the piers that are the supports, I guess, call them piers, 1 and 2. What's the force of the floor or the earth or something like that on the diving board at those 2 points? Is it F1 is up, F2 is down? They're both up. F1 is down and F2 is up. Or it could be something depending on the mass of the man and the length of the board. You use your intuition here. I'm going to work it out. I'll try to work it out 2 different ways depending on where I put the rotation axis. But let me give you a minute to think, pair, and share.
We have a question from the previous solution. Where did you get L over 6 from?
Oh, yeah. Yeah, I think I did half minus a third. This is it's got to be halfway, right? So xm plus L over 3 equals L over 2. Common denominator. L over 3 minus 2. Good question. Now that's in the notes. Whoop. So thanks for that. You guys got a guess on this one? Let me see 144. Oh, there we go, 260. Okay, 5 seconds. Click in. 4, 3, 2, 1. This one is pretty controversial. Oh, again, almost stopped the session. Stop delivery. But half of you voted that F1 is down and F2 is up. And I agree with that one. And I'll show you why. It depends where you put the rotation axis, but it doesn't matter actually where you put the rotation axis, you'll get the same answer either time, but the calculation is going to look different depending on where you choose your axis. So let's choose, for this one, rotation axis equals 1. So let's do that. It doesn't matter where you, but let's put it there for now. Okay, so what do you have? You have, F1's not going to matter for the torques, but you're going to have F1, let's just put them both up, because I don't know them. There's also going to be the gravity of the board, I think, M of the board down, and there's going to be, on this one, the mass of the man gravity, because there's a normal force of his foot sort of pushing down on the board, choosing the system to be the board. Equals board. So the man's an external normal force pushing down. So you've got the sum of the torques is equal to 0. That's going to be F1 times 0. And then this F2 will be, if it's up, it'll be a counterclockwise torque. So plus F2 times X2 or something. And then minus MBG, call this like XB, and this X man or something like that, times XB minus M man G X man. So that's okay. I would say that you've got F2 X2 equals some mass, some positive number plus a positive number, XM, all times a positive number G. F2 must be greater than 0 for this to work, for the torques to cancel. So that's okay. And then the sum of all the forces in the y direction is going to be F1 plus F2 this is going to get weird. I guess what I could do is I could choose, if I choose the rotation axis as 2, I was about to work this out, but it's going to be, then I would say that the F1 is torque is clockwise. I'm messing this up. Is clockwise if it's up. But the other gravities are going to be clockwise as well. So I think F1 has to be down. So, sorry about the messing this up, but this is, so F1 is negative. So the other thing that I was going to do is say that I was going to try to work it out, which is to say, again, let's just put the axis right there. And again, we have that x2 times f2 is equal to m of the board times x of the board times g plus mass of the man times x of the man times g. So f2 is equal to something, mbxbg plus mmxmg divided by x2 So I'm going to say that that's greater than the mass of the board times G plus the mass of the man times G for some reason. And then the sum of all the Y forces is going to be just F1 plus F2 minus M board G minus M man G. And I get F1 is equal to M board G plus M mass G minus F2. And that's going to be less than 0. So I also got C there. So basically, if you have numbers and you work it out, if you choose both forces to be up in your diagram, which is fine, then you always find that F1 is a negative number and F2 is a positive number.
Quick question.
Yeah.
Why are we looking at the mass of the board if it says that the mass of the board is negligible?
Oh, there you go. That's probably why this got so messed up. So if you cross that out, does that make a little more sense? X of the man is greater than X2. It's farther away. This is X2, and this is X man. So if we neglect the mass of the board, then we can see why since XM, that's a really good point. Since XM over X board is greater than 1, then since you're taking the mass of the man times G times XM over X2, I don't know what's going on with me today. That's why that's bigger. And then we're taking mass of the man times G minus F2. We know that this is bigger than this. Sorry, F2 is bigger than this. So that's why that's negative. So thank you very much for that. Whoever typed that in sort of saved me there. Okay.
One more question.
Yes, please.
So does the rotation axis not matter? They ask because we set it at both 1 and 2 during different parts of the question. So does it not matter where it is?
Yeah, it's exactly. That's it. So that's the whole point of static equilibrium problems, is that it's not rotating. So if something's not rotating, it doesn't matter what you choose the rotation axis is. It's not rotating about any axis. It's a really good point. Okay. Yeah, I wanted to do this next one. So let's go through a little bit of a biology problem, and then I'll set you guys free here. But when you hold a ball in your hand, the bicep muscle tenses up and pulls the forearm up around this rotation axis, which is on the left. And if you turn your hand around and push down, then what's happening is that your tricep muscle pulls up on this side to the left of the rotation axis and wants to rotate your arm clockwise. So equations of equilibrium allow you to estimate the muscle tension forces if you're worried about tearing a muscle or something. So the problem-solving strategy, if you were asked, for example, what is the force of tension of this muscle on your forearm, and you know the weight of your forearm and you know the weight of this ball, you can, I guess I'll do this when we come back because we still have that Monday. You can choose your forearm as being your object and list all of the forces on it. Okay. I'm clearly losing you guys. I will get back to that forearm thing when we come back. Everyone's standing up to leave. I want to say have a great reading week. I hope you do something sort of non-school related. I've listed 3 suggestions. You can see a drag show at El Cavanto Rico, which I've done. That's always fun. you go salsa dancing at Lula Lounge. They usually have a salsa lesson sort of around 7 o'clock for people like us who want to learn salsa, and then they go crazy at like 8 o'clock. Or you could go to the art gallery if that's more your style. There's a couple really good shows on. Okay, guys, you obviously have someplace to be, so have a great one. Take care.